Share screen. All right. First of all, I posted up on Slack earlier, but I'll announce it here. On April 17th, which is a Saturday, from 8:30 a.m. to 8:30 p.m., the department through the Hackathon Club is having a app hack where they're going to be writing, doing a 12-hour computer programming competition. I'm requiring it for all of my classes. If for whatever reason you aren't able to attend, work obligations, something like that, there will be an alternate assignment, but the best way to meet the requirements will definitely be to attend the hackathon. I think there will be options for attending it remotely as opposed to having to come physically to campus. So whatever your comfort level is, that is fine. I think we can accommodate. But in any case, mark your calendars for Saturday, April 17th, and then also reach out to Jonathan to get your name on the list to make sure that he has an idea of the number of people that are attending both physically as well as remotely, and we can figure out food and all that jazz. All right, questions about that?
Yeah, I have a question. Am I allowed to go to that?
Yep,
I'm not a
absolutely.
CUW student.
Yeah, you are in fact cordially required to go to it. So you you are certainly welcome to do it remotely. We'll make it work. But if you want to road trip it, you can certainly come on over. But yes, this is for all of our students, not just ones that are here on campus.
All right, thank you. Because it just says CUW everywhere and CUW student, so I felt.
Yeah, and part of the problem is it's just the historical way that we say it. So I mean, now it's where technically our university name is what CUWAA, Concordia University, Wisconsin, Ann Arbor, or something like that. So historically, we've just always said CUW for Concordia University, Wisconsin. You guys have always said CUAA for Concordia University, Ann Arbor. Technically, we are one university now, so it's whenever you see either of those, you can just read them together because you're a student at the same university as all the other people here are a student at. You just attend at a different campus. All right. Any other questions about that guy? All right, so then let's go over and look at the rest of our homework assignment, then start. I think I said we were talking about shared memory today, I believe, but let's finish our thing with our ROT 13. All right, let's see where we left off with that guy. I'll put those up here in a few minutes. All right, so last class we let's see, what was the actual homework assignment? To finish writing our convert to encode ROT 13. So encode ROT 13 string, finish writing this function. Let me minimize this such that it returns a new string, which is the S encoded in ROT 13. You should use old school pointer math whenever possible. Okay. So we know the length of our string that's being passed in. So encode ROT 13 string is taking in a string as a parameter. We get the length of that string by calling our function we wrote last time, string length. That's going to give us the number of characters in that string. Then we're going to go ahead and create our new string using memory allocate. And how much are we going to allocate? We're going to allocate the number, and this allocates a number of bytes. So we're going to allocate this number times the size of a char in bytes, which is 1. So it'll give us enough bytes to hold this string. Now, actually, let me think about that. Our string length returns the number of characters in a string, not including the last \0. So actually, we probably should say a +1 there to give ourselves the one extra byte of memory to hold the \0 in as we're building this guy. Okay. In fact, we can even start off by terminating our string at the very end, although we'll do it at the very end as we walk through it. All right, so we have a pointer now, answer, which points to the beginning of a chunk of memory that is related to, well, that has the same length as the chunk of memory associated with S. So we want to walk through all the characters in S, encoding each one of those guys. Let's see, where did we wrote an encode character, right? 13 string length. Oh, here. Yeah, so we wrote encode rot13. So go get rid of that. So now we have our function. This takes a single char and spits out a single char that is encoded. So we want to call this function one time for each bucket of for each character in our string S. All right, so I'll go ahead and get rid of this stuff. So we're going to go through every element of S. So we're going to say for int I is equal to 0, I is less than length, which happens to be the length of S, as well as the length of answer, I++. Each time through, we want to get a character. So I'll just say char temp here. And we'll say that temp is going to equal encode rot13. And we need to pass this guy a char. What char are we going to point it or pass it? We're going to pass it the value found at S plus I. So this is the character that we find at bucket I of our string S. So this would be S plus 0 the first time, S plus 1, S plus 2, S plus 3. The star in front of it says, give me the char that lives at that bucket. All right, so this guy will boil down to the char at bucket I and S, which I'm then passing to encode rot13, which then spits out as my answer temp, which is the encoded character. I then want to put that encoded character at bucket I of answer. So we'll go ahead and say answer, the value at answer plus I is equal to temp. So we'll store inside of answer plus I the value at that memory address. We'll store in the value temp. All right. Lastly, we'll say star answer plus length is equal to our \0. And then we will return answer. All right, so that's the string we built that lives in memory. We'll return a pointer to that guy. And there is our encode rot13 string. We'll go ahead and test this now. Let's see, so I already have, here's our test for the map thing. And then we wrote get rid of these couple of things here. So we're gonna, right now we're encoding hello, and then we're gonna print out the encoded string for hello. So this should be hello encoded. Does that look correct, everybody? I'm guessing a Y, an L encodes to Y. That sounds right. All right, so that is, and if I take that string URYYB, URYYB, and I encode that guy. I get hello. So I think that covers the homework, right? So any questions about this guy? We used old pointer syntax as often as we could because we definitely want to stay in the mindset of using working with memory. So this guy right here is equivalent to a line that looks like this. That. And similarly, this is answer at bucket I is equal to temp. These two lines mean the same thing. But we want to steer clear right now of working with this convenience syntax because this syntax is going to give us practice in working with some of the things with shared memory and some of the other interprocess communication stuff we're going to look at that deals with specifically walking memory, and that's going to be a little bit more uncomfortable for us right now. All right. Oops, sorry. So questions about this homework assignment? All right. So before I go on then, let me just test this real quick, make sure I didn't just break anything. All right, good. And then I'm going to do a push to GitHub real quick, just so you have the all right. So I already have a couple of other programs here that we're going to kind of walk through today and then see them work. But one of the things we're looking at initially, we're going to have kind of two pieces here because we're going to create a protocol around it. We want to look at this idea of shared memory, and then we also want to look at the idea of signals. Today it's just shared memory. Okay. Let's see, where am I? Here. So shared memory. Now, one thing we want to consider here is that we're going to say that shared memory does not dictate the memory space that is being shared in terms of user space versus I don't know what, root space, admin space, kernel space, that's what we've been using. All right, so the starting point for that is it would be dictated based on the context of where the program's running. So if we have a computer program that's requesting shared memory and it's already running inside of kernel space, that shared memory without additional flags would be housed in kernel space. Similarly, if we had something that was in user space, the same thing would be true. It would be housed in user space. If we have a program that's bridging user space to kernel space, we would have to do some extra stuff in order to properly map shared memory between processes that live in kernel space and in user space for them to communicate with each other. And we've kind of already seen that a little bit through that, those two functions that allow you to bridge across from user access, from uaccess.h, that allow you to bridge across kernel space and user space. So we might look at an example of that, but right now we're thinking about this just from the generic perspective. So the generic perspective of shared memory is create a named place in memory that two processes, we'll say presumably living in the same user or kernel space can use to share, let's call it shared data. All right, so that's the goal of shared memory. Remember, when we're talking about it's a little concerning rainbow wheel thing spinning there. We'll see if it works itself out. When we're talking about inter-process communication, what we're talking about is the ability for two different running programs, two different processes, to somehow communicate with each other. And there's different forms of communication. We first talked about this before the exam. You know, if you're like out at a playground or something like that, and you want to get somebody's attention, you might, you know, yell like, hey, and wave your arm or something like that. And for an example like that, we're not really sharing large amounts of data. I haven't just given that person, you know, the email address or something like that. You know, I've gotten their attention. I've notified them of that I'm interested in talking to them or something like that. And we're going to look at that through something called signals. Similarly, we mentioned the idea of, let's see if this guy, how dead he is right now. Yeah, definitely struggling. Okay, similarly, if we want to have a direct connection between two processes, and you had looked at sockets versus pipes previously. So if we want to have a direct communication between two processes, we can actually almost, you can think of it like making a phone call, where those two processes link directly to each other and they are tethered together and share information back and forth. All right, so that's another thing that we will look at, seeing that in practice. But what we're going to look at right now is this idea of shared memory. And well, I'm going to let that keep cooking over here because it seems like, I wonder if iCloud is having issues right now, but that's okay because we're going to look through some code over here. All right, so we're going to look at two programs that kind of each latch onto a place in memory. So they're not directly communicating with each other. Instead, they're picking the same place in memory. I think I maybe initially talked about this as kind of like a little, like a drop location or something like that, where you know, somebody put something, you know, under a rock somewhere, and then somebody else can come up, and if they know about the location of that rock, they can go and lift the rock up and retrieve the information that was there. All right, so we do this through shared memory, which is like a named variable that lives in memory somewhere that two or more processes can both get at. So let's initially look at this through an example. So I have two different programs. I have a writer and a reader, just to show us the two different sides. So let's look at the writer first. All right. All right, so the writer, this is going to generate a unique key. So we have this function called ftoke, and I'm going to see if there's a man page for ftoke. So convert a path name and a project identifier to a system5 IPC key. So unique ID for this path, this place in memory, something like that. All right. So coming back here, we're going to use this function, which lives in shared memory.h. Actually, I'm lying. That function lives in IPC.h, I believe. Yeah, he lives in IPC.h. Because this guy isn't specific to shared memory. He's specific to generating a unique identifier, okay, for inter-process communication stuff. So it's used in some other examples of inter-process communication. All right, so what does this guy do right here? He creates a key type, and this is, since it's an underscore T, this guy, look at that. So if we hover over it, it actually helps us. Whenever you see something that has an underscore T on it, it's a special kind of type, but it probably means something much more simple. So if I hover, notice this guy is just an integer. So this is going to generate a unique integer surrounding this string as a shared memory file, which we just made up. We could have called that elephant or something like that. And that second function here is an ID that both both of our programs are going to agree on. So we've just hard coded a 65 in here. So we're saying, look, I want to get a unique identifier for a place in memory named shared memory file with my project ID of 65, wherever I pulled that from. Okay. So this is going to give us just a unique identifier for this place in shared memory. Then I'm going to actually get some shared memory. And what am I going to do? I'm going to pass it the key. So this is shared memory get. Come out here. So allocates a System5 shared memory segment. System5 is kind of old Unix. It was called System5 Unix. And on top of that, we've had evolutions of Unix that now move towards what's called POSIX. But POSIX doesn't change the Unix compatibility piece. It just changes, like with POSIX, everything's a file, things like that. So whenever you see System5, you pretty much know this is talking about something that has been in Unix for a while. So this isn't some newfangled tool that came out, 6 months ago or something like that we're learning about. Hence the reason why we're looking at trying to do all of our examples using old school pointer math, because we're going to run into some examples here where sometimes we'll be forced to do old school pointer math because anything more evolved than that didn't even exist when these things came out. All right. So shared memory get, this gets us, this allocates memory. So a shared memory segment. You can kind of think about this as like malloc for memory allocation, but instead of allocating memory under the ownership of the current running process, we are allocating memory under the ownership of interprocess communication at the operating system level that can presumably be shared among two processes. We're going to be seeing a writer and a reader today sharing these two things. All right, so we'll say shared memory get me some memory. Oh, what are we linking this to? I want it to be linked to this unique key that we generated above here. And we're going to see, I'll actually just jump over real quick. Notice when I generate my key and my reader, I'm doing the exact same dude. So these two are going to map to that same key. That's the secret, right? They know the string, and they also know their process or project ID that they've agreed upon. They've decided this is code name project 65 and in this example. All right, so shared memory get requires you to pass it. Go back out here. A key, the size in bytes of that shared memory, and then any flags. Let's see if it shows us examples of flags. So this is anytime you see all caps, things like this, that's probably a macro, and that's defined somewhere. It's probably just a string somewhere. So we can be creating a new shared memory. So this creates a new segment. So this guy, I'm guessing that stands for excludes. So this is like IPC create, but what it does is it'll fail if it's already been created. So then we have other things that we can send in as flags. But effectively this says, I want to create some shared memory of this size surrounding this unique identifier, and these are the rules I want it to play by. Okay. So we come back over here. We're going to say, look, I want to, actually, this is a good example here for our bitwise ORing. So shared memory get key, I want 1024 bytes, which is, we're going to get 1 kilobyte of memory. That's what this guy's grabbing us, right? 1024 bytes is 1 kilobyte of memory. And now what we're doing is we're passing this flag, but this is called masked data. Masked data. And we can actually see, I'm interested in what IPC create is real quick. Well, here, can I get it from the, I'll just do it right here. We'll say printf %d IPC create. run this real quick. So it's 512 is that guy. All right. We don't know why. We just proved that IPC_create is the number 512 for whatever reason. All right. So this is going to be the number 512. So it's a macro that ultimately produces this integer, and that integer has a meaning for whatever reason. This guy 0666, that is the, well, what do you think this guy is referencing for this shared memory?
Is it like read, write, and execute?
Well, yeah, so it's the permissions for it. 666, I think, is read write only, not execute. But yeah, it's setting the permissions of that shared memory. So we're taking this number and we're bitwise ORing it with this number. What does bitwise OR mean? So if I take, let's see if this guy's up and running again. Yep. No, he's still in his deathbed. So if I have 0666 bitwise OR with, what was it, 512? What does this guy equal? What is it actually giving us? What's this math that's going on here? What kind of answer is this going to be? Cat, dog, or integer?
Ooh, integer.
I was gonna guess that Proctor was gonna come up with that one. All right, so this is gonna give us an integer, and ultimately, what is it going to do? We're gonna take here. Let me just cheat here real quick. It's a fairly unfortunate. Okay, so this is the binary version of that guy. Bitwise OR with. Oops. Oh, I should have been able to do that one. That was an easy number. So it's really doing bitwise OR of these guys, which ultimately is going to bitwise OR these two things. So bitwise OR says to do what? How do I bitwise OR these two numbers together? We had to do another cat dog example. Okay, so just like a normal OR, where in C-based languages, a normal OR uses two vertical bars, a single vertical bar says bitwise OR. This guy is called, what we're doing here is called masking. So we're taking these two numbers and we're masking them together to give us another number, and that number has a meaning. We don't know what that meaning necessarily is, but the permissions, this last piece here, this guy right here boils down to a single value, a single integer that has some meaning in terms of the exact specifications for the shared memory get that we're currently looking at. All right. So to bitwise OR things together, we go per bit. It's bitwise, and we OR them together. So 1 or 1. Remember, with an OR, it's one or the other or both. So if we have at least 1, 1, the whole thing's a 1. The only time it's a 0 is if both are 0. So 1 or 1 is 1. 0 or 0 is 0. 1 or 0 is 1. 0 or 0 is 0. 0, 1, 1, 0, 1, 0. And I can do the math for that, but let's just cheat real quick. Binary 2 decimal. 66610. This guy equals 66610 for the answer to this. So my feeling is that this the way they're interpreting this answer, they're probably going to split it out to get the individual pieces. This guy is read, write, execute for the owner, read, write, execute for the group, read, write, execute for everybody else. and then these next two together are going to equal the create versus one of the other flags that we were looking at. So those two guys get kind of squished together, mixed together in a bowl, and it gives us a single value like this, which has meaning. All right, so this is how masking works. How we're interpreting this value isn't up to us. It's still going to be up to that shared memory get function, where he's going to look at this single number and decide, oh, well, what am I dealing with there? Well, he can take this single number and he can do a, what it would be a bitwise and on these pieces, the first part to get just that value. Otherwise, he can do a shift to shift everything right to get, oh, actually, he would do a bitwise and on the whole thing, getting that value. Otherwise, you can shift right twice, then do a bitwise and to get just that value. So these are our ways of extracting information from those values. We don't have to worry about this for us. I'm just kind of giving you an explanation of what the heck is going on with this. All right. As a human being, we can read this and say, oh, we're setting up some permissions as well as I also want to create that interprocess communication thing. Okay. So questions about that? I would say that bitwise ORing is something that you should be able to do. It's not a hard thing, but it sounds intimidating when you first hear it. All right, so questions about this guy. What I'll do is, just since Keynote's acting funky right now, I'm guessing there's something going on with iCloud. I'll just throw that in there as a comment, just so you kind of have the, what the heck is this thing? All right, but punchline here is we're getting some shared memory associated with this unique identifier. How much shared memory are we getting? A kilobyte. All right, and what's going to come out of this is a unique ID for that shared memory. This is the magic. We're going to use this tool in order to get at that shared memory. All right, so now we're going to create a string. So what happens here with shared memory is we've now created a place in memory that's shareable. We've given ourselves a way of talking about this between two processes doing the same crap we just did up here, right? You know, we generate the same key, we get the shared memory associated with that key, and now two different processes, in our case here, our reader and our writer, are both talking about the same plot of land in shared memory. But ultimately, we now need a mechanism for communicating across that plot of land, all right? And we do that through shared memory attach, schmat. All right, so this guy attaches to a shared memory segment. And what are we going to do? We're going to get a pointer to a string, and I don't like when it rates it like that. All right, but we're going to call shared memory attach, and let's look at the return type for shared memory attach is a void pointer. All right, so this guy is a pointer, but it's a generic pointer that doesn't associate type to it. When we associate type to it, we're dictating how we're going to use that memory. All right, so I'm saying, look, I want to attach to some shared memory. Which shared memory? This dude right here. Okay, my shared memory ID that I figured out up here through shared memory get. Okay, then I'm passing it two more parameters. I'm passing it a shared memory address and then any sort of flags. So if we give it a null value, which is what we're doing here, it's just going to choose a suitable unused page aligned address to attach the segment. So effectively, if we give it a 0 here, a null value in C, it's going to say, okay, operating system, I need you to go figure out where's a acceptable place to put this. All right. And then it'll do that for us. All right. Then the flags, similar to what we had before, we can do this for, read only, things like that. We can flag it for different things to kind of give us the settings for that guy. All right. So we're going to say, I want to attach to some shared memory. This is the shared memory ID I want to attach to. I don't care where you put it, but just put it somewhere that's appropriate. That's what that piece says. And then I'm saying, I have no special permissions I want to associate with this. Just give me plain Jane generic shared memory. All right. And this is going to ultimately boil down to a void pointer. It'll be the base address of that shared memory as a void pointer. I'm going to go ahead and cast it to a char pointer instead of a void pointer. I'm going to put a question in here again, since Keynote is doing something. Is it still doing something funky? Oh, no, we're seemingly back. What is the difference between a void pointer and a char pointer? So what practical difference does that make? So if I have, we'll just use our real example here. I think it'll let me copy it from there, paste it over here. Yep. So if I say void pointer V is equal to that dude, as opposed to the same line here, what's the difference between these two? Or how can you explain the difference between those in terms of how they will work? Hint, hint, it's probably going to avoid memory walking, because that's what we've been focusing on. That's why we did old school pointers in the last assignment. What do you think the difference between those two is? We have no guesses. Who's even online today? I want to see who's online. One of you is capable of guessing at this.
Is it like the size? Because a char would be like a byte, and you wouldn't know the size for a void.
Okay. Okay. So good. So the question here is if I say, well, here, we'll just do it. V plus 3. This is going to equal what? Versus string plus 3. These won't necessarily give us the same answer. I'm doing pointer math with this. Now we know that a char pointer has size 1. So when I take 3 steps off that base address, yeah, see, this is still happening. This is still struggling here. When I take 3 steps off that base address from string, I know I'm taking 3 byte size steps. But how big is a void pointer? Okay, how big is a nothingness? I don't even necessarily know the answer. I'm guessing a void pointer, I wonder what the default step size would be. I'm guessing it's either 4 bytes or 8 bytes, probably 4. Okay, but in any case, we don't know. We don't. It would probably be dictated by the default settings in the memory manager. Okay, but we do know how big a char is. So a char is 1 byte. So if I typecast this to a char pointer, and then I tell it to take char pointer size bytes, or char size steps as I walk through memory, because I'm storing this guy inside of a char pointer named string, when I add 3 to it, it will take char size steps. If I don't store it inside of a string, I store it in a void pointer, it's going to take however big a void step is, which I don't know. We could probably figure it out. You know, it's going to be whatever it's going to be. So since we're walking through a string here, we're going to have this guy as a char pointer. So that's why we've made this decision to go ahead and say, I want to take this void pointer that you gave me, and I want to treat this as a char pointer. I'm not changing the memory. This dude's still going to give me the base address of a chunk of memory that is 1,024 kilobytes big. I'm sorry, that is 1,024 bytes big or 1 kilobyte big. Okay, this dude's giving me the base address of that. All I'm doing is I'm saying, you know what? When I take steps through that, I want to take char size steps. So I wanted to convince you that he's actually a char pointer, and I'll store it inside of a variable for this char pointer. All right. So now what does this program do? It's going to ask us, so I'm reading something in. So this is scanf. I'm going to read a string in from the end user. So, you know, we're saying, what data do you want to write? We'll read something into the string str. Okay. Now str, this guy is a local string, but that is attached to shared memory. So when I read it in here, I'm actually reading it into a place in memory that is shared with some other program that might read from that same place in memory. All right, then we'll go ahead and say, hey, we wrote this to memory, and then we'll go ahead and detach from it. And this program can then end. I go into reader.c. Notice we're doing something pretty similar. We're getting our same token. We're doing shared memory get, the same thing we did before. So we should get that same shared memory ID. We're attaching to it. So we're giving ourselves a local string that is our mechanism to talking to that shared memory. But then we're going to go ahead and we're just reading from it. So we're going to print out whatever value we found in string, which is the value that was stored in that shared memory, which was written there by a different program. All right. So I'm going to go ahead and I'm going to do a GCC writer.c, and then I'll do a -o writer. That way the executable will be called writer. And I'll do GCC reader.c -o reader. So now I have my 2 executables. So I'll go ahead and do a /writer. So I'm going to write something to shared memory first. What am I going to write? I'll say LOL elephant. All right. Now notice here it says, oh, what I've written there is LOL. Okay. When you use scanf, scanf reads tokens until there's a space. So I wrote LOL space elephant. If I wanted to read in 2 separate things, I would have had to do %s%x. So in this particular case, it just read in the LOL into my string that I then wrote to shared memory. So now we'll go ahead and run our reader. And our reader is now reading from that same place in shared memory. We used the same token to get us there, yada, yada, yada. And it said, oh, look, I found LOL there. Now what happens if I run reader a second time? It didn't find anything there. So when somebody writes to shared memory, it's there until somebody reads from it. But when somebody reads from it and then closes that shared memory, the data that was handed off is now no longer there. All right, that makes some sense?
How would you preserve the data that's there? Are you going to talk about that?
Well, if you want to preserve it in shared memory, you actually have to write it to shared memory differently. So that's shared memory is perpetual. I think we will do, it's a different flag for this guy. When you get the shared memory, you're not just creating it, you have to get it a different way, I believe. I can look at that here real quick and see if well, actually, here's the difference. It's inside of our reader. We're doing this. We're destroying that shared memory. I think if I just don't do that, if I choose not to destroy it, it would still be there. That was in my reader. So I'll say writer. We'll say hello. Then I'll do reader. I get hello. If I do reader again, it's still hello. So
that's kind of how you clean up the memory.
So this other guy, yeah. So shared memory CTL. It's controlling shared memory. So man. So this is memory control. And what are we giving that guy here? We're giving it the ID we want it to do, and then we're giving it the thing that we want to do to it. So this is the message so this is our controller. It can do all sorts of things with shared memory. The specific thing we want to do here is we want to remove that identifier. We're unlinking that shared memory so that it never existed. And down here, I'm assuming they give us a list of the different things we might want to do. All right, so for your homework, am I live back over here now? What we want to do is we want to now merge these two pieces together. So we want to, for homework, update our ROT13 program to write a message encoded in ROT13 to shared memory. Let's call this ROT13 writer program. And our ROT13 reader program should read from shared memory and decode the message that was encoded in ROT13. All right, so we're just taking all the different abilities we've already written and we're putting them together inside of a, I'll read something in from the user, I'll encode it into ROT13, I'll write it into shared memory, then the other program will read from shared memory, this ROT13 encoded thing, it'll decode and spit it out to the screen, and here is the secret message. Something like that for right now. Make sense what I'm asking you to do for Wednesday?
I have a question.
Oh, go ahead.
So I'm assuming this is like a one string type of thing because you said the scanf does one string.
Single
right?
string. Yep. Single string using scanf right now. So just one word. CSC450. Actually, I need to be back one level. I'll go ahead and push this to GitHub so you have the latest version of this code, but I would encourage you to incorporate it into your own versions rather than just copy mine. But in any case, for Wednesday, we should have the ability to have two programs share encoded messages with each other through shared memory. Questions, comments, concerns, bribes? All right, I will see everybody on Wednesday.
Gracias, senor.
You're taking the place of Noah. I think he's on vacation. He's going to watch recordings this week.
Yo, it was an honor of him. All right, see ya.
Later.